Hello, welcome everybody. In this video we're going to compare two distributions, the hypergeometric distribution and the approximation using the binomial. And for that we just need to do a very simple transformation on the estimating parameters. So let's talk about the hypergeometric distribution. This distribution has four parameters. That is, there is a sample, there is a lot, so to speak, the size of the lot of usually denoted with big N. Then you have a number of successes in the lot, that is the total possible successes. Think about you have a bag of 10,000 marbles and some of them are red, so the number of the lot size is 10,000 and the number of red marbles is the number of successes that you're interested in knowing. So let's call that capital X, and you're going to take a sample. So the sample size is a small n, which has to be, of course, smaller than the big N. And then you can compute the chances of, inside that sample size, you have how many successes. And of course, it has to be the number that is smaller between the total number of successes in the lot and the sample size. It cannot exceed any of those, and we're going to see. So the number of successes in the lot, in the sample, we're going to get the successes in the sample, we're going to know with small x. Well, since we're using a spreadsheet, I'm going to just use S because small s, to make a clear distinction, because maybe the font the successes of the lot from the successes of the sample. So now Excel gives you, that's a rather long computation because it depends on a lot of combinatorics, and the combinatorics have a lot of factorials. But Excel has this prepared for you as the hypergeometric distribution. Hypergeometric distribution. And the parameters are starting to be spelled out. The first one is the sample successes, so that would be this cell. Then the number in the sample, that's the sample size, that would be that cell. Then the population successes, and finally the number in the population. So in a way it's going backwards with respect to my logic. Alright, and now everything is 0, probability is 100. But let's say that you have a lot of 200 and the number of successes in the lot is 23. And now the sample size, let's say that the sample size is 10. And you're interested in knowing the success in the sample being exactly 0. You have a probability of that happening, of having exactly 1, having 2, etc. Now it'll be a little complicated to have all these maybe repeated, but not so much if we have the possibility of doing this. The number of successes will vary from 0 to n. In this case, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Those are the possible answers, and we can use this formula here. And the only thing we need to change is the first parameter, which right now is E9. All the others can remain fixed, so what I'm doing is I am making a reference call to the parameters, an absolute reference call to the parameters lot size, number of success in the lot, and sample size. And for purposes of the reading of the sample successes, I'm just going to go to the number here to the left, and then I can copy this formula, and that's it. That would be the hypergeometric distribution. If we wanted to compute the cumulative, well, we can just start with 0 and then keep adding the previous result to the new result in this way. So at the end of the day, the last few numbers are not 0, but for all practical purposes is so small that it's very unlikely that you will have that. Now this would be the hypergeometric mass function, and then this is the hypergeometric. I'm gonna just type hypergeometric. Very good. So the question is, how do we compare now with the binomial? The binomial has different parameters. The binomial has the number of trials and the number of successes, but it doesn't have a lot size and doesn't have a number of successes in the lot. However, what we can do is we can estimate a probability of success by computing the p value of probability of success at a single step. This would not be very precise over time, because as we go withdrawing some of these items from the sample, the parameter p would change. Here we can keep the n being 10, and next we can vary the x also from 0 to 10, just like with the hypergeometric. But the parameter p, how do we determine the parameter p? Well, an initial estimate of a good p would be the 23 divided by 200. And the answer that we have at that moment is 11.5%. Again, it's not that it's independent as is the assumption in the binomial, but it's a good approximation for a lot size that is large enough. So we do the binomial again. Let's see, binom. And the number of successes is the number here. The number of trials, it's always going to be 10. And the probability of success, that. And I'm going to go with false for purposes of cumulative. The binomial can give you directly the cumulative, but I am not going to use that this time. I'm going to use the same way as I did with the hypergeometric. There you go. Now the numbers are not going to be exactly the same because it's an approximation. They are not way too off. You see, if we compare this column to this column, it is very close. We can actually prepare a graph. Let's prepare a graph. For that, I'm going to just bring the data from those columns. I'm going to use the I'm going to prepare one for the mass function, and this is the binomial. Let's see, side to side, the difference is not to insert the graph, and you see they are almost on the same. There is a gap though, but it is close enough. So it's a good approximation, I would say. I mean, without going into the details of running a test. And if I do a similar graph for the cumulative, I skip one number. Yes, I skip 8. What we can see is that I'm going to grab the hypergeometric value, and I grab the binomial cumulative value, and now I can make a graph. I like the way that looks. Let's see. And it's so close that you cannot even see the difference. Although, believe me, there are two lines there, but it's so close that. So it's important for us to know that, because in some cases the computation of the binomial is significantly easier than the hypergeometric, when we have to compute all those large numbers. So take that into consideration, and this is how you compare them at this level. I hope you find it useful. See you in the next video.